So yeah, hey everyone, I'm Morten. I'm the manager here on the blockchain team at Zama. We're a smaller team within Zama, focusing on building components for using encryption on blockchain. And today we'll be running through our fhEVM, which is our solution for executing these, expressing and executing these contracts. Okay, so everything on the typical blockchain is public, which is good for transparency, but as we also know, has some issues around privacy. So for instance, since you can see the balances of everyone, that might open you up as a target for potential criminals. You might also not be comfortable with everything you do being easily monitored. And finally, there are some inefficiencies around things that you can take advantage of when you have all this information. For instance, MEV, where bots are trying to basically take advantages of transactions you make. So our solution to this is using fully homomorphic encryption. I won't go into details with this, especially for this group, but the general idea, as you probably know, is you can compute on data while it remains encrypted. So you can, for instance, have an encryption of X, an encryption of Y, then you can do a homomorphic operation on these and obtain a third encryption, which is now an encryption of X plus Y. Likewise, you could have an encryption of X, Y. You can do a homomorphic comparison between the two, and then without decrypting, arrive at a third ciphertext, which is now a bit indicating whether or not X was smaller than Y. And more generally, you can take a bunch of ciphertexts, you can apply a function to them homomorphically, end up with a new ciphertext, which is now an encryption of this function applied to the plaintext of the initial ciphertext. So what we do with this in the blockchain setting is we can encrypt both the inputs to transactions and to view functions, and also the state on the blockchain. Since we're encrypting everything, and I'll go into a few more details about this, but since we're encrypting everything under the same key, we get a very nice composability. So you can, for instance, you build your distributed application using different contracts, and then have the contracts call each other like you would in a normal service-oriented architecture. And you can also mix data from different users. So this is useful, for instance, if you're building an auction or voting and so on. We're not changing, as we'll see here in the coming slides, we're not changing everything about how blockchains are working, about how smart contracts are working. So it's very easy to add this to an existing infrastructure. We'll have one example, for instance, where we see that we basically introduce new data types into your contract language, which are encrypted data types, but you can use these together in your smart contracts together with plain text data types. Okay, so some of the use cases we're focusing on with this is, the first one is tokenization. So it's this idea that you can represent various assets on chain, from blockchain assets all the way up to real world assets. And then you want to exchange these or swap these around. In this case, you can use confidentiality to encrypt the amount of data that's being swapped, or amount of tokens that's being swapped around. As I said, you can also build auctions where you can encrypt what you're bidding for, or sorry, not how much you're bidding for an item, and even who the winner of the auction is. We can do on-chain gaming, poker, for instance, where we can generate randomness, and then we can play the whole game with encrypted state and only reveal the winner at the end of the game. Voting, where you can encrypt who you're voting for and also how much voting power you're putting on your candidate. We can do something around identity solutions, where you keep your attributes encrypted and on-chain. And when you want to prove to someone that you're above a certain age, for instance, you can do this on-chain using homomorphic operations instead of having to do custom zero-knowledge proofs. And finally, of course, we can do things like ERC20 tokens, where you want to hide your balance, you want to hide how much you're transferring between different users. As we'll see, we're not trying to hide what you're computing. So the smart contract code is completely public, but what we're doing is we can encrypt the data, keep the data confidential, that the smart contracts are computing on. There are many ways to obtain similar results, and here we have a brief comparison between some of them. So the first one is to other encryption schemes compared to the TFHE that we're building here at Zama. One is we have the benefit that we can do any operation using lookup tables instead of just additions, multiplications. Another one is that since bootstrapping for our scheme is very fast, it means we can do we can keep computing on the data. We basically never run out of steam. The other one is we can do exact computations. So if your balance today is a certain amount, then you're guaranteed that is also the balance tomorrow without any differences there. Compared to, for instance, using zero-knowledge technology to arrive at a confidential solution, One benefit of fhE is that we can keep all the data on-chain and encrypted, and we can also compute on it on-chain. So for instance, in zero knowledge, you need, in order to do the computation, you need to have all the data that you're computing on in plain text somewhere, and then do the computation in plain text, and then submit a proof that you did that computation correctly. But if you're building, for instance, an auction, then that means someone needs to see all the bids in order to figure out who is the winner. With fhE, of course, we can just compute directly on-chain on the data without revealing anything to any particular entity. And then finally, compared to, for instance, secure enclaves like XGX, we get the mathematical guarantees as opposed to having to rely on the hardware manufacturer. Some of the features of our solution is that we can get precision, very high precision of integers, up to 256 bits. We have a floor of operators that's available for the smart contracts. We can use conditional statements, also known as CMUX in some cases, or in typical academic literature, where you can basically, you can do an oblivious branching in your smart contracts. We can generate secure randomness on-chain, so useful in gaming, for instance. We have various options for protecting the keys involved in the computation, either centralized or using threshold protocols. And then, as I said before, since we're using TFHE underneath, we can do very fast bootstrapping. So we get unbounded computation. We basically never run out of steam for using the data, which is, of course, very useful on the blockchain, where you don't know how many times your data is going to be used, how many times your contract is going to be invoked, and so on. Okay, so to dig in a bit about how this stuff works under the hood, we're combining a lot of different cryptographic techniques. Of course, fully homomorphic encryption, which is used for all the computation. MPC, which is used in our key management solution, where we have threshold protocols for decryption. And then also some zero knowledge proofs, as we'll see, around the inputs for security, both from a cryptographic perspective, but also from a systems perspective. So the general setup is that everything on an fhE chain is encrypted under the same global fhE public key. So the black dots here, they represent validators in a blockchain. And we assume that they have this black key, which now all the data, all the inputs and all the state is encrypted under the same key. So this is where we get this nice composition where if one contract calls another contract, well, then since the data of the two is encrypted under the same key, then they can freely share that data. Since two users are encrypting the data under the same key, then it's also very easy to use this, to mix this in a computation, for instance, in the blind auction. So we have one global key that's available to everyone. And then, of course, the question is, where does this key come from? We have threshold key generation, where the validators or the initial validators are starting out with nothing, and then they generate secret shares of this particular, of a global key, and each hold on to a share. And then using a typical secret sharing schemes, we get the guarantee that on their own, none of these validators can learn anything. But if they want to use the key, then they need to enter it into or participate in a threshold protocol where their share of the key is then used. When users want to provide input to the blockchain, in this case here an X, they simply encrypt under this public key, and then they give a proof that the encryption was done correctly. And they send this to the validators so that they now have this encryption of X. When the smart contract says, okay, now we want to compute on the values of the states that's available on chain, then we use the homomorphic operations. Basically, the smart contract calls into our fhEVM, which then calls into, or is executing in the fhEVM, which then calls into our homomorphic library. So taking an encryption of X and encryption of Y, then the validators can individually use our encryption scheme to arrive at an encryption of Z. When they want to decrypt, as I said, we have a threshold decryption protocol. So in this case, the validators have the share of the decryption key. They have an encryption of X. They each jointly decide using the smart contract logic, we'll see in a bit, that, okay, now this ciphertext needs to be decrypted. So they participate in the decryption protocol and arrived with now everyone knowing the plaintext X. We can also do another thing which we call re-encryption. So this is useful, as we'll see on the next slide as well. If a user wants to read the data of the blockchain, then we could use decryption, but then that will make that data available to the entire world, basically. So if we're talking about a balance of an ERC20 token, then we can do a re-encryption instead, where in addition to the black global key, we also have a user-owned blue key. So in this case, we have the blue key, which is known by all the validators. We have the ciphertext of X, which is known by all the validators. and then they enter a threshold re-encryption protocol, which then turns the encryption of X under the black key into an encryption under the blue key. And in that case, of course, if the blue key was owned by the user, then they can call a view function to download this blue ciphertext and then do the decryption on their own because they know they own the key and obtain the plaintext without leaking anything to the validators. Then to dig into a bit about how you express these smart contracts, this was a bit about how this worked behind the scene. And then on the smart contract developer side, the first thing we do is we introduce these EUINs, so encrypted unsigned integers. And now you can start using these instead of using typical UINT32, so instead of using plain text data. So for instance, if you're building an ERC20 contract, you will typically have a mapping between addresses and balances, or encrypted or in integers. And now you can do this mapping between addresses and encrypted integers. So they represent an encrypted value that can be used for computation, for storage, for giving to other contracts as part of composition. And they're quite efficient to pass around because they're essentially just handles to ciphertext. We currently in the library have support for 8, 16, 32 bits. As I mentioned before, we can the underlying homomorphic library supports all the way up to 256 bits. So we'll be adding this in the future as well. We have support for various operations, add, multiplication, comparisons, and so on. Then the other thing that's worth pointing out is that there is this difference between the EUINT, which I said was basically a handle to the ciphertext, and then to the actual ciphertext. So when data is coming into the blockchain, it comes in the raw bytes of the ciphertext together with this proof we saw before. And then in order to compute it or to convert it into something that can be used for computation and for storage, you need to do this conversion. So as EUINT32. What we do here is we check that the proof underneath is correct. So we check that it's a well-formed ciphertext, and we also check that the generator of this ciphertext, the user that sent in the ciphertext, actually knew the underlying plaintext data. So we're doing this to prevent a user from going on the blockchain, grabbing an arbitrary ciphertext, which is publicly available, and then sending it into a smart contract to have it decrypted. By insisting there is a zero knowledge proof, and by having him prove that he knows the plaintext, then we kind of circumvent the user from using the blockchain as a decryption oracle for data that he can pull down from the blockchain. Okay, then we have a re-encrypt method where we take an EUINT32 and a public key that we want to have it re-encrypted under. So in this particular case, we're using a salt key where the user will say, okay, I want to see my balance, but I don't want anyone else to see it. I don't want the validators to see it. So the smart contract is saying, okay, this is a re-encryption from the ciphertext encrypted under the global key into a ciphertext or a value encrypted under the user's public key. When he gets this back, he can then use salt to decrypt the value. We don't dictate how if you want to authenticate the user, if this is in a view function where there's generally no signature. But this is very easy to work together with other signature schemes. For instance, a typical developer of this contract might say, okay, I want to have a signature on the public key that is actually coming from the message.sender in this case. So you're linking the identity of the owner of the account together with the public key that's coming in so that no one can cheat in that way. But again, we leave this up to the smart contract developer to decide how they want to manage access control. And then finally, we have a decrypt operation where you're revealing the plaintext to all the validators. So in this case, for instance, you have a typical require that if you want to make a transfer in an ERC20 token, you want to require that there's sufficient amount on your account before you transfer it to someone else. So you can evaluate the condition homomorphically, arriving at an encrypted bit, decide to decrypt that bit, and then require that the bit is true. Of course, this leaks something. This leaks the bit, and it's really up to the smart contract developer to figure out what leakage is allowed, and ultimately the user to say, okay, do I want to interact with this smart contract, or is it leaking too much of my data? So as an alternative, you can also use a CMUX or this kind of encrypted if-else, where you still evaluate the condition homomorphically, and then you evaluate both cases, both if this was an encrypted true or an encrypted false, and then you mix those together to arrive at the result. So in this case, there's no failing. This operation cannot be aborted. The downside is that you're paying for both branches, both the if branch and the else branch, but no leakage. So what we end up with here, we have I just put everything together here as an encrypted ERC20. There is a link to a website where you can go see more of these examples. But what we end up with is basically a developer experience, which is very close to what you would do on plain text data. You just have these new data types. You have these extra operations that you need to use. And for instance, in the example here, we can see that the balance of function, we added some custom access control logic that says that only the sender. So whenever the sender wants to see his balance, he needs to do a re-encryption under a key, and there needs to be a signature on this key that matches with his identity. And likewise for transfer, in this case, we're saying we keep everything encrypted, but we leak 1 bit about whether or not there was sufficient amount on the account to do this. And then, yeah, we can go and try this for yourself. We have various GitHub repositories, documentation, Docker images, and also a white paper where we go into details about how this stuff works. All right, let's open up for questions.